Hello everyone, this is lecture 49 for the mathematical physics. In the last lecture we were discussing about the integrals which have singular points on the real axis. Okay, and we find this method, and I already explained you completely this method, that how to find the integral of this kind. Okay, so you need to consider a contour which encloses, means just making a I over contour over this point and make this closed contour and solve this, then it can give you the integral. Okay, so we find these two results for the particular example. Now let's summarize this step. Means if you need to find a integral, then fz dz will be equal to minus infinity, this is principal value, means except that point at which it is singular, plus I over, that is the value of this contour. We already find this value, this is nothing but minus I pi, and the residue of fz at z naught. So this I over plus this C2 contour, this one. So this is your integral. Now with the help of this expression you can find the value of this one, because this can be calculated using this residue, and this will turn out to be 0. Then this will be equal to this, simple. And you know how to find this complex integrals. That is a very simple thing. You just need to find the residue at all points, and 2 pi iota multiplied by residue will give you the value of this. So that's how you can find value of this using this. Okay, now so this is the result. What is the value of this? 2 pi iota residue other than z naught will give you this. Now you can take this kind of contour also, means here you are taking this I over. Now you can take I under, means you can take this point inside the contour, means you can make this like this. Okay, this kind of contour can also be made like this. Then what will the change in this result? In place of I over, you will write I under, and it will be I by a minus 1, not a minus. Okay, just sign change, and here the residue will remain same. And now what you will do, means now in the integral of this, residue will be find it at this point also. Means here you are taking the residue other than z naught, because this point was not included in the contour, but now it is included. So you will find this 2 pi iota residue other than z naught plus residue at that point. So that will be the value of this integral. Now from here also you will write the value from directly, and this integral turn out to be 0. Then you can find this fx dx. So there we have two methods. So you can either use this one or this one. This is more comfortable. Okay, so this can be used only sometimes when in the question it is given that use the I under, or this kind of contour is given, only then use this. Okay, so let's see some more examples. I equal to minus infinity, you need to solve this cos mx divided by x minus b dx. So I already told you, whenever you are getting cos or sine inside the function, then just assume fz as exponential imz divided by z minus b. In place of x, just write z, and cos and sine write the exponential function. Because in the last we can just separate these real and the imaginary terms, and you can compare them to find the value of this. So z equal to b is a simple pole. Here we can see this, z equal to b is a simple pole. So let's find the residue at z equal to b. It will be z minus b, it will cancel out. Here it will give you exponential imb. Now use this formula again. So this will be 0, because this is kind of 1 upon z minus b, and means here see, this is fz, and as z tends to infinity will turn out to be 0. So from the Jordan's lemma condition, this term will be 0. Okay, and I over will be minus I by, and what is the residue we have find it? It is exponential imb. So this will be this condition. Now see, there is no singularity in the plane other than this z equal to b. So value of this will be 2 pi iota multiplied by residue, this will be 0. So this complete is 0. So value of this will be equal to I by a minus 1, and this residue is exponential imb. So value of this is equal to this. Now see, we can separate these real and the imaginary term from here. So cos mx plus I sin mx. So from there you can see, means this can be written as I by cos mb minus pi sin mb. So real term will be equated to this, and imaginary term will be equated to this. So that's how you can find this. Means after comparing, integral value of this will be pi cos mb, and integral value of this will be minus pi sin mb. So that's how you can solve. Now though similarly try to solve this question also. I equal to 0 to infinity sin x divided by x square plus a square dx. You need to prove this equal to this, pi by 2a square 1 minus exponential minus a for a greater than 0. Now what you will do to solve this integral? You will just in place of sin x you will write exponential iz, and in place of x you will write z, as I already told you. Then you will solve this. The singular points will be z equal to 0 and z equal to plus minus iota a. Okay, because at these points this is not defined. So when you find the value of means now you will apply this formula again. So for the fz dz you will find the 2 pi iota multiplied residue. So other than this point there is also plus iota lying inside the contour, so it will be 2 pi iota residue at this point equal to this one, means I over will be minus I pi and residue at 0, so you will find this. Then this contour will be 0, so that's how you can get the value of this fx dx. And when you will get this exponential ix, then it can be distributed or separated in cos x plus sin x, so that's how you will get the value of sin x. So you can solve this similarly as we already discussed many examples. Only difference is in the left hand side, in place of fz dz you won't take 0 here, you will find the value of this integral with the singular point plus iota I, because this is lying inside the contour. In the previous examples we don't have any singular points inside the contour, so that is the only difference, otherwise it's same. So just know the concept, okay, understand the concept, only then you will be able to solve any kind of questions which will be related to this. Okay, so focus on concept. So let's say we have this example sin 2x by x cube. Now how to solve this kind of question, because we were discussing the single pole till here, till here, but now it's not a single pole, it's a pole of order 3. So how to solve this? So first we have to convert this in the this kind of expression which we already know. So how can we convert this? So see, it's a simple thing. First, limit a tends to infinity minus a to a, means we just write it this one as this, means a equal to infinity. Then we can write this this thing as equal to this, limit a tends to infinity minus a to a sin 2x by x cube, where a tends to infinity. Now let's say this 2x equal to u, some other variable u equal to 2x, then x will be u by 2, then substitute here, dx will be du by 2. So after substituting these values here you will get this integral, limit a tends to infinity minus 2a to 2a sin u by 2 whole cube du by 2. Now limit a tends to infinity 4 minus 2a to 2a sin u by u cube d cube. Now you have this expression, use the by parts, integration by parts. So take this sin u as first function and 1 upon u cube as second function, and let's see what we will get. So we are getting this first function, integration of second will give you minus 1 upon 2u square, then limit minus differentiation of first function will give you cos u, then 1 upon u cube will give you this. Now this is your first, then separate this. Now apply again the by parts on this, cos u will as it is, this is first function, integration of second function will give you 1 upon 2u plus now the differentiation of first function, that will give you sin u, and this one. Now see, you can solve these because you have the limits and they will be turned out to be 0 because it tends to infinity. Now how you solve this? Now see, you have u in the denominator and this is a pole of single order. Okay, so single pole you have. Now you can apply the formula which you already know, and a tends to infinity, so it will be minus infinity to infinity sin x upon x, that kind of thing you will have. And we already defined this, that 0 to infinity sin x by x, and dx is nothing but pi by 2, and this can be written as 2 0 to a or 0 to 2a, so that is 2 into pi by 2. And then you have this 4 outside, this 4 outside, and this 1 upon 2 outside. So you will have this expression, that will be value of this, because these two will be 0 because this limits, infinity limits, so this will be equal to 2 pi. So what I do here, I just converted this third pole 3 order integral into the form of the single pole, which we already know how to solve. So that's how you will use this thing which I told you to solve the integrals. Now let's see the last topic for the complex analysis, that is branch point singularity. So only what you need for the exam I will tell you, okay, because this is a very vast topic. So what is the meaning of branch point singularity? That means it is this is defined for only those functions which have multi-value, okay, multi-valued function. Like this is singularity uniquely associated with multi-valued function. So see, let me give you an example. Like you have under root of z. Now for every value of z, like z equal to 1, you will have plus 1 minus 1 value of this function. For z equal to 3, you will have plus 3 minus 3, or sorry, under root plus 3 minus under root 3. So you will have two values. for every kind of this z value. For z equal to 1 you have plus minus 1. So this function is defined and it has multi-value. So that's why this kind of if singularity associated with it, with this function, that is called the branch point singularity. So let's see why we are calling this branch point singularity and what is the meaning of branch point. Because branch point for this is 0 and infinity for this kind of function. So how we define this? Let me first tell you in brief. Let's say we have take z equal to 0 as origin and made a circle of unit radius. Okay. And now see, first you have at this theta equal to 0, this value is 1. Means z equal to r exponential I theta for circle, you know, and modulus of r equal to 1 because this is a unit circle. So z equal to exponential I theta. Now for theta equal to 0, this will give you 1. Now let's traverse this path along this circle. For this pi by 2, you will have value of fz as 1 plus iota by root 2. For this pi, theta equal to pi, you will have this value iota. For this 3 pi by 2, you will have value as minus 1 plus iota divided by root 2. Now you reached this point again and this theta is 2 pi and you will have the value as minus 1. So see, you are having two value for the same point. Okay, so that is the meaning of multi-value. Okay, and that's how the singularity associated with it is called the branch point singularity. Now any point like 2, for 2 also you will have 2 different points. For 3 also you have 3 different points. Means whenever 0 is inside this circle, you will have all those points have 2 values for this kind of under root function. Okay, just like if there was a cube root, then you will having 3 values. For 4, 1 upon 4, you will have 4 values for the same point. So that's how this branch point is defined. Okay, now this 0 is included, only then you are getting this kind of thing. Because for 0 there is no 2 values, this is a single value. Means only at z equal to 0 this function is defined or differentiable or analytic. Okay, otherwise it's not. So this z equal to 0 is nothing but branch point for this kind of functions. Because if you take this circle outside, and means this you take this 0 outside this circle and make it like this. Now you can pass a ray to this point and you will see that it can't go to 2 pi. Means when it is go to here theta, then it will go from here, negative or positive. This theta won't be 2 pi ever. Means it will always remain theta 0. And now what you did, you just make this function as single valued by taking this 0 point outside. Okay, means see, this is the angle. So if you are measuring this, it will go up to here only. Then again if you are measuring here, it will go here. So it is never gonna be complete circle because this is not inside. So that's why now every point in this have the single value. Okay, so it is, now you did what you did, you made this function single valued. So that's why we call this z equal to 0 as branch point for this kind of function. Okay, because this is acting as a branch and this ray must be passed through the 0. That is the reason. Okay, that z equal to 0 is a branch point singularity. So that's how I told you that why z equal to 0 is a branch point singularity. Now any fz equal to means what is the order. So the after how many path you are getting the same value, that gives you the order of singularity. So for this one under root z, the order will be 2, because after one circle and two circle you will get again, when it will be 4 pi, you will get again one value. Okay, first you have 1, then first circle you have minus 1, after second circle you will have 1 again. So that's how you will say that order is 2. If it is n, then order will be branch point singularity, order will be n. So just remember that z equal to 0 is a branch point singularity, and I already told you why. Now order of the branch point is defined as number of paths taken by the function before reaching its original value on or initial value. So I already told you what is the order, means how many rounds you have take to come to the first value again. So that is the order. Now see, if you have this kind of function fz equal to log z, so log z equal to 0 is a branch point singularity, and what is the order will be. So you remember from my lectures, in the previous lecture I already told you how to solve this integral. So value of this integral is log r, that is mod of z, plus iota theta plus minus 2n pi. So for n equal to 0, 1, 2, 3, 4, 5, 6, you will have infinite values for this fz. Now here you are having only 2 values for fz, but here you will have infinite values. So that's why order will be infinite order, because it will not come to again the first value it at infinite times. Okay, it won't be come again to this value, that's why order is infinite. So remember this. that what it means, only this kind of only this square root, cube root and log function will be asked for the branch point, not more than this in your question papers. So we'll discuss only those things, and there are some results also. Fz equal to z minus alpha a, z minus beta b. So z equal to alpha means now you know z equal to 0 is a branch point singularity. So every function which have this kind of thing you will try to make inside 0. So at z equal to alpha this will be 0. So means this will be branch point singularity when this a is fractional and z equal to alpha. And here also this will be branch point when z equal to beta and this b is fractional. Because if b is integer, then this won't be your multi-value function. Okay, just you can see here, if you take this fz equal to z or z square or z cube, then this won't be a branch point, means you are not getting a multi-values, you will get a single value for that. So z equal to alpha is a branch point if a is not integer, and z equal to beta is a branch point if b is not an integer. Means it must be fractional to make it branch point. And z equal to infinity is a branch point if a plus b is not an integer. So remember this result. If a plus b is not an integer, then this z equal to infinity will be in your branch point. So let's see one example. So fz equal to this. So for z equal to 0, what is the branch points? So z equal to 0 is the branch point singularity, and z equal to 1 is the branch point singularity, because these powers are not integer. And for z equal to infinity, if we wanna try, then we will add these powers, it will give you 1. So that is integer. So that's why z equal to infinity is not a branch point. So that's how you can determine. Okay. So that's it for today. Just try to digest this thing. Then in the next lecture we'll move forward. We'll see some more examples related to this. Then it will be more clear to you. Okay, then thank you everyone.